Characteristics of meteorological parameters on fair weather days. To study the characteristics of AFs during fair weather, a clear definition of the concept of fair weather is essential. Harrison et al. Defined fair weather conditions as those without any type of hydrometeorological phenomenon, with visibility exceeding 2 km, no low-level clouds below 1500 m, and near-surface wind speeds of less than 7 m per second 1920. Later defined fair weather as conditions where the cloud cover in the sky is less than Mach 8, the wind speed is less than 4 m per second, and there is no precipitation. 21. Israelson et al. During atmospheric electric observations at the Master Observatory in Sweden considered weather conditions with electric field values between 0 and 0.25 kV/m as fair weather because of the lack of corresponding meteorological data. 22. On the basis of the definitions of fair weather mentioned above, in this study, we established the following criteria for fair weather. 1. The weather is clear throughout the day. 2. The total daily precipitation is 0. 3. The average visibility throughout the day is greater than 20 kilometers. This definition ensures that the selected data accurately reflect the stable characteristics of the AF without significant interference from meteorological phenomena. According to this criteria, and after excluding anomalous AF data, a total of 67 days that met the conditions were selected for study during the period from September 10, 2021 to December 31, 2024. The daily measurement values for this data were averaged to obtain the corresponding average values at each time point, as shown in Figure 1a. The horizontal axis in the figure represents local time UTC+8 with the left red vertical axis indicating RH. The red curve represents the average RH at each measurement time, and the error bars represent the corresponding standard deviation. The right blue vertical axis indicates the temperature, with the blue curve representing the average temperature at each measurement time, and the error bars representing the corresponding standard deviation. Figure 1 shows that RH exhibits distinct temporal variation characteristics, being higher in the morning and evening and lower in the afternoon. The maximum RH occurs at approximately 8 o'clock, whereas the minimum is at approximately 1600 hours. In contrast, the temperature trend is the opposite of the humidity trend, being lower in the morning and evening and higher in the afternoon. The minimum temperature occurs at approximately 8 o'clock, whereas the maximum temperature occurs at approximately 1600 hours. Figure 1b shows the correlation relationship between the average temperature and RH. The figure shows that there is a strong correlation between temperature and RH with a correlation coefficient of approximately -0.9970. This indicates an inverse relationship between temperature and RH. When the temperature is high, the RH is low, and when the temperature is low, the RH is high, reflecting opposite trends. The linear fitting relationship between temperature and RH is as follows. In other words, for every 1 degree Celsius increase in the average temperature, the average RH percent decreases by approximately 4.08. Figure 1. A. Daily average variations in temperature and RH on fair weather days, and B. Their linear relationships. The correlation coefficient is -0.9970. Full-size image. Figure 2. A. Polar plot of the wind direction and wind speed, and histograms of the statistical results of B. Visibility, C. RH, and D. Temperature on fair weather days. Full-size image. Figure 2 presents the statistical results of the meteorological parameters over the 67 days, where Figure 2A shows a polar plot of the wind direction and speed, Figure 2B is a histogram of visibility, Figure 2C is a histogram of RH, and Figure 2D is a histogram of temperature. In Figure 2a, the polar plot illustrates the wind direction and speed, with the magnitude of the wind speed represented by the radial distance from the center to the point. The angle of each point indicates the wind direction, and the distance from the center represents the wind speed, with the wind speed being the maximum hourly wind speed. The plot shows that during fair weather in the Cheongong area of Kunming, the wind direction primarily falls between 180 degrees and 270 degrees, indicating a southwesterly wind. Statistical analysis of all the wind direction data revealed that the frequency of wind directions between 180 degrees and 270 degrees accounted for 87.75% of the total sample size. This means that during fair weather, the Cheongong district of Yunnan province predominantly experiences southwesterly winds. Coupled with the characteristics of humidity changes, we can infer that during these times, the humidity from the southwest is low, which does not lead to significant fluctuations in humidity. In Figure 2b, the histogram of visibility shows that the time with visibility greater than 20 km accounts for 95.27%, indicating high visibility. For RH, values between 0% and 30% are defined as dry, 30 to 50% as comfortable, 50 to 70% as humid, and over 70% as very humid. Only 20.58% of the data show a humidity greater than 70%. Additionally, temperatures above 10 degrees Celsius account for 76.33% of the sample. The unique geographical location and meteorological conditions of Changong District result in distinctive daily variations in temperature and humidity, which ultimately lead to corresponding changes in the atmospheric electric field. This will be discussed in detail in the following section. Diurnal variations in AEFs on fair weather days. For the AEF data, we applied Gaussian filtering for smoothing on the 67 days of electric field data and then sampled and extracted hourly measurements at whole hours to calculate the average electric field values at each corresponding hour, along with the standard error. This resulted in the daily average variation characteristics of the AEF during fair weather, as shown in Figure 3a. Figure 3a shows that the daily average AEF at the station exhibits a W shape with the following characteristics. The electric field values range from 0.12 kV/m to 0.22 kV/m. The first trough occurs at approximately 8 o'clock, after which the values gradually increase, reaching a maximum at approximately 12 o'clock. The values subsequently gradually decrease, with the second trough occurring at approximately 1700 hours, followed by a gradual increase. After 2000 hours, the electric field stabilizes, remaining between approximately 0.2 kV/m and 0.22 kV/m. Figure 3b shows the daily variation characteristics of PM 2.5 and PM 10 on fair days. Figure 3b shows that the daily variation patterns of PM 2.5 and PM 10 also approximately exhibit a W shape. The first trough of PM 2.5 occurs at approximately 6 o'clock, with the second trough occurring at approximately 1600 hours, whereas the first trough of PM 10 occurs at approximately 7 o'clock, and the second trough occurs at approximately 1500 hours. Figure 3c shows the diurnal variation of solar irradiance. The irradiance values remain at 0 between midnight and 6 o'clock. Starting from 7 o'clock, there is a noticeable increase, reaching its maximum value at 1300 hours. After that, it begins to decrease and gradually returns to 0 after 1800 hours. From the perspective of change trends, between midnight and 7 o'clock, both the AEF and the PM 2.5 and PM 10 concentrations monotonically decreased. Between 1700 hours and 2300 hours, the AEF and the PM 2.5 and PM 10 concentrations monotonically increased. From 7 to 1700 hours, although both the AEF and PM 2.5 and PM 10 initially increased but then decreased, the AEF reaches its peak at 12 o'clock, whereas PM 2.5 and PM 10 reach their peak maxima at 10 o'clock. Compared to the variation characteristics of PM 2.5 and PM 10, the trend of irradiance between 8 o'clock and 1700 hours shows a striking similarity to the variation trend of the AEF. Figure 3. Daily average variations in the AF, B, PM 2.5 and PM 10 concentrations, and C, irradiance on fair weather days. Full-size image. To investigate the correlations between AF and various parameters such as irradiance, PM 2.5, PM 10, and RH during different time periods in detail, we divided the study period into 3 segments based on the diurnal variation characteristics of AF and irradiance, midnight to 8 o'clock, 8 to 1700 hours, and 17 to 2300 hours. We calculated the correlation coefficients between AF and each parameter for these 3 time periods, as shown in Figure 4. Figure 4 illustrates the correlation between AF and irradiance during 8 to 1700 hours. Figure 4b shows the correlations between AF and PM 2.5, PM 10, and RH respectively during midnight to 8 o'clock. Similarly, Fig 4c depict the correlations between AF and PM 2.5, PM 10, and RH respectively during 17 to 2300 hours. In Figure 4, we observe that during midnight to 8 o'clock, the correlation coefficients between AF and PM2.5, PM10, and RH are 0.8842, 0.8376, and minus 0.7676, respectively. Between 8 to 1700 hours, the correlation coefficient between AF and irradiance is 0.8962. During 17 to 2300 hours, the correlation coefficients between AF and PM2.5, PM10, and RH are 0.9268, 0.8995, and 0.9339, respectively. The AF demonstrates significant correlations with various parameters, such as air pollutant concentrations, RH, and irradiance, across different time periods. To investigate the relationships between AF and various parameters, we calculated their correlation coefficients using the daily average values. The specific results are shown in Tables 1 and 2. Table 1 presents the correlation coefficients for each parameter over the entire day, midnight to 2300 hours. Table 2 provides the correlation coefficients between AF and different parameters during specific time intervals. Since the solar irradiance approaches zero during the periods of midnight to 8 o'clock and 17 to 2300 hours, the correlation coefficients between AF and irradiance were not calculated for these time intervals. Table 1 correlation coefficients between RH, maximum wind speed, visibility, PM2.5, and PM10. Full-size table. Table 2 correlation coefficients between AF and different parameters during different time periods. Full-size table. From Table 1, it can be observed that RH exhibits a high correlation with maximum wind speed and visibility, with correlation coefficients exceeding 0.9. Furthermore, based on the results in Figure 4, RH also shows a certain level of correlation with AF. Therefore, we believe that AF may also exhibit some degree of correlation with maximum wind speed and visibility. To quantitatively investigate their relationship, in this study, we calculated the average of the absolute values of the correlation coefficients between AF and PM2.5, PM10, RH, maximum wind speed, and visibility during midnight to 8 o'clock and 17 to 2300 hours, as well as the correlation coefficient between AF and irradiance during 8 to 1700 hours, marked with star in Table 2. The resulting average correlation coefficient is C equals 0.8654. Therefore, we define that in the analysis of the correlation between AF and various parameters, an absolute correlation coefficient greater than C equals 0.8654 indicates a strong correlation, while an absolute correlation coefficient smaller than this value suggests a weaker correlation between AF and the respective parameter. Based on this criteria, the following conclusions can be drawn from Table 2. 1. During the period from midnight to 8 o'clock, AF exhibits a strong positive correlation with PM2.5 and maximum wind speed. 2. From 8 to 1700 hours, AF shows a strong positive correlation with solar irradiance. 3. Between 1700 hours and 2300 hours, AF demonstrates a strong positive correlation with PM2.5, PM10, and RH, and a strong negative correlation with maximum wind speed. Figure 4. Correlations between AF and various parameters. A shows the correlation between AF and irradiance during 8 to 1700 hours. B, E, D depict the correlations between AF and PM2.5, PM10, and RH respectively during midnight to 8 o'clock. C, F, G illustrate the correlations between AF and PM2.5, PM10, and RH respectively during 17 to 2300 hours. Full-size image. We believe that during the period from 1700 hours to the next morning at 6 o'clock, the lack of sunlight means that the main factor affecting the AF is the concentration change in aerosols caused by PM2.5 and PM10. Polluted aerosol particles adhere to ions in the atmosphere, reducing conductivity, and this increase in the AF is a result of Ohm's law 23. When the concentrations of PM2.5 and PM10 are high, the aerosol concentration is also high, which allows more charged ions to be absorbed, leading to a decrease in local conductivity. Conversely, when the concentrations of PM2.5 and PM10 are low, the aerosol concentration is low, resulting in fewer charged ions being absorbed and an increase in local conductivity, thereby decreasing the electric field. The Figure 3 shows that at approximately 8 o'clock in the morning and 1700 hours in the afternoon, the AF begins to increase. This may be related to peak commuting times. During peak hours, high emissions of automobile exhaust lead to increases in the concentrations of the air pollutants PM2.5 and PM10, which in turn increase the aerosol concentration. This results in aerosol particles adhering to ions in the atmosphere, reducing conductivity and ultimately causing an increase in the AF. Between 8 o'clock and 1700 hours, the AF initially increases and then decreases, which aligns with the trend of irradiance. The irradiance exhibits a parabolic variation trend between 8 o'clock and 1700 hours, while from 17 to 6 o'clock the following morning, the solar irradiance is minimal and can be essentially neglected. During this period, changes in the atmospheric electric field can exclude the influence of irradiance. We believe that this is due to atmospheric thermal convection and turbulence induced by irradiance, leading to fluctuations in near-surface water vapor and aerosol concentrations, which in turn affect the AF 23, 24, 25. Starting from 8 to 12 o'clock, as irradiance increases, surface temperatures rise, enhancing atmospheric thermal convection and turbulence, while human activities also contribute to the gradual increase in aerosol concentration. From 12 to 1700 hours, due to a decrease in air pollutant concentrations, along with a decrease in irradiance at approximately 1300 hours, the aerosol concentrations gradually decrease, leading to a reduction in the AF. After midnight each day, human activities diminish and diurnal temperature changes enhance the ability of thermal convection and turbulence in the lower atmosphere to transport aerosols upward, reducing aerosol concentrations in the lower atmosphere. This results in an increase in the conductivity of the near-surface atmosphere, ultimately causing a gradual decrease in the AF 24, 26, 27. Seasonal variations in AFs on fair weather days. To study the seasonal variation characteristics, we group the selected atmospheric electric field data according to seasons. Spring includes March, April, and May, summer includes June, July, and August, autumn includes September, October, and November, and winter includes December, January, and February. The filtered atmospheric electric field data for each season are shown in the Table 3. Table 3 number of fair weather days from September 10, 2021 to December 31, 2024. Full-size table. We extracted the corresponding meteorological data along with PM2.5 and PM10 data for the same time periods to conduct our study. We found that during spring and autumn, there is no obvious correlation between the variations in the electric field and the diurnal variations of PM2.5 and PM10. However, in winter, the trend of electric field variation is highly consistent with the variation trends of PM2.5 and PM10 concentrations, as shown in the results of Figure 3. We believe that the different seasonal variation trends are mainly due to the strict filtering criteria we applied to the fair weather electric field data, which resulted in a relatively small number of qualifying data points. As a result, the sample sizes for spring and autumn were insufficient, leading to less pronounced trends. Conclusions. This study selected AF data, meteorological data, then PM2.5 and PM10 air quality data from 67 fair weather days in Chiangong District, Yunnan Province between September 10, 2021 and December 31, 2024. The analysis revealed that the daily variation patterns of PM2.5 and PM10 during fair weather approximately exhibit a W shape, with the first row for PM2.5 occurring at approximately 6 o'clock and the second occurring at approximately 1700 hours, whereas the first row for PM10 appears at approximately 7 o'clock, and the second trough occurs at approximately 1500 hours. The daily average changes in the AF on sunny days were also analyzed. The AF in Chiangong District follows a W shape with values ranging from 0.12 kV/m to 0.22 kV/m. The first trough occurs at approximately 8 o'clock, followed by a gradual increase, peaking at approximately 12 o'clock and then decreasing again. The second trough occurs at approximately 1700 hours, after which the field gradually increases, stabilizing at approximately 2000 hours at approximately 0.2 kV/m to 0.22 kV/m. We studied the correlation between AF and PM2.5, PM10, RH, maximum wind speed, visibility, and solar irradiance. The study found that 1. During the period from midnight to 8 o'clock, AF exhibits a strong positive correlation with PM2.5 and maximum wind speed. 2. From 8 to 1700 hours, the AF shows a strong positive correlation with solar irradiance. 3. Between 1700 hours and 2300 hours, the AF demonstrates a strong positive correlation with PM 2.5, PM 10, and RH, and a strong negative correlation with maximum wind speed. Methods. Acquisition of meteorological data. Meteorological data are fundamental for analyzing the relationship between AF disturbances and meteorological parameters. This study uses meteorological data from the Chengong Meteorological Station in Chengong District, Kunming, Yunnan. The coordinates of the Chengong Meteorological Station are 24.90889 degrees north and 102.8269 degrees east with an elevation of 1971.4 m. This station provides meteorological data recorded hourly from midnight to 2300 hours each day. The research in this paper utilizes meteorological data from September 10, 2021 to December 31, 2024. This period's meteorological data helps us analyze in detail the impact of weather conditions on the AF. The data can be downloaded from the website https://q-weather/weather/56882/. Due to missing meteorological data, we used the meteorological data corresponding to 66 fair weather days for our study. Electric field data measurement. The electric field measurement data are obtained via an electric field mill EFM 28, 29, 30, 31. This instrument measures the electric field by utilizing the induced charges generated by a conductor in an electric field, which consists of a moving plate and an induction plate. The working principle of the electric field mill is as follows. The moving plate is driven by a motor to rotate, and when the vertical electric field lines strike the induction plate, charges are induced on the induction plate 32. As the moving plate rotates, when the electric field lines are blocked by the moving plate, the charge on the induction plate becomes 0. If the moving plate continues to rotate, the induction plate continuously outputs an alternating current signal, with the amplitude of this signal being linearly proportional to the electric field strength. The alternating current signal output from the induction plate is converted into an alternating voltage signal through the IV current voltage conversion of a preamplifier circuit. The induction signal is a sinusoidal waveform, and by measuring the current magnitude, the strength of the electric field can be inferred. However, this alternating signal cannot determine the polarity of the electric field. Therefore, a reference signal synchronized with the induction signal is generated in the sensor, allowing the use of a phase-sensitive detector to detect the polarity of the electric field 28, 29, 33. The electric field mill used in this study is installed on the roof of the School of Physics and Electronic Information at Normal University, which is located at 768 Jushian Street, Chengong District, Yunnan Province, as shown in Figure 5. Its coordinates are 24.86 degrees north and 102.86 degrees east, with a straight line distance of approximately 6.38 kilometers from the Chengong Meteorological Station. The measurement range of the instrument is plus or minus 50 kV/m, with a measurement accuracy of less than 5%, a response time of less than 1 second, linearity of less than 1%, and a measurement resolution of less than 10 V/m1. Continuous measurements of the AF were conducted from September 10, 2021 to December 31, 2024. Figure 5. Locations of the Chengong Meteorological Station, CMS, Electric Field Mill, EFM, and Solar Radiation Measuring Instrument, SRMI. The map in this figure was generated using MATLAB, R2024b, and MATLAB is available at https://www.mathworks.com. Full-size image. Irradiance data measurement. The solar irradiance data is sourced from the TYD-YG5 Solar Radiation Measuring Instrument, SRMI, which measures direct solar radiation, total radiation, and scattered radiation within the spectral range of 0.28 micrometers to 3 micrometers. It is installed beside the EFM with an approximate straight-line distance of about 5 m, as shown in Figure 5. Due to missing irradiance data, we used the irradiance data corresponding to 36 fair weather days for our study. PM 2.5 and PM 10 data. The PM 2.5 and PM 10 data are sourced from the National Air Quality Real-Time Release Platform of the China National Environmental Monitoring Center. The data can be downloaded from the website https://codesoft.net/air. Due to some missing air quality data, we used the PM2.5 and PM10 data corresponding to 66 fair weather days for our study. The combination of this electric field data with meteorological data and air quality data provides a solid foundation for analyzing the coupling relationship between AF disturbances and meteorological and air quality parameters. Through comprehensive analysis of the data, we can identify the relationships between meteorological factors, air quality factors, and AF, reveal the complexity and temporality of AF disturbances, and lay an important foundation for a deeper understanding of the coupling relationship between AF's meteorological factors and air quality factors. Data availability. The electric file data used and or analyzed during the current study available from the corresponding author on reasonable request. References: Leigh et al. Fair weather near surface atmospheric electric field measurements at the Junction Chinese Station in Antarctica. APPL Sci 12 and 9248 2022. Article Math Google Scholar. Li, W, San, Z, Yen, Z and Mart, Z observations and variability of near surface atmospheric electric fields across multiple stations. Atmosphere